Hello and welcome to episode 3 in the series Calculus 101. And today we're going to be solving a few examples using the Epsilon-Delta Limit Definition. I do recommend that you check out my previous episode in the series, which does cover the formal definition of the limit, which will be required to solve these problems. Let's get started. Just a small recap, this is what we did in the previous episode. This is just a simple graph where x can never equal a, the function is undefined, where the limit as x approaches a of f of x equals L, and therefore to restrict x, we must say that the absolute value of x minus a must be less than some value delta, where this right over there can be treated as delta, and f of x minus L, where L is the limit, must be less than epsilon, where this value right over here is epsilon. Once again, just a quick recap. So now let's try and do a few problems using that definition. So where do we actually use this definition? This definition is used only in proofs, in proving that a limit equals this. How do we prove it? Let's do an example. This is an example that we have right over here. The limit as x approaches 3 of 5x plus 2 equals 17. You can solve it pretty easily, just plug 3 into the equation. But what I want to do is actually prove this limit. Or if not prove, find a value of delta given a value of epsilon. Once again, if you remember my analogy in the previous episode, I gave you the analogy of a two-player game where the first player provides the second player with a value of epsilon, such that the second player can find a respective value of delta. So that's basically what we want to do over here. So how do we start? The first thing that we have to do is start with those absolute value signs such that we can restrict x. So the first thing that we can see is this can be treated as f of x, this can be treated as a, and this can be treated as L. So in the general form, we can now say that the absolute value of 5x plus 2, which is f of x, minus L, which is minus 17, must be less than some value of epsilon when the absolute value of x minus 3, which is treated as a, must be less than some value of delta. So let's start off with the epsilon value first, because that's usually where we start off from. So we can now evaluate this guy to absolute value of 5x plus 2 minus 17 is minus 15, must be less than epsilon. So we can simply factor out 5 and we can say the absolute value of 5, the absolute value of x minus 3 must be less than epsilon. So now we can say x minus 3 must be less than epsilon over 5. This looks surprisingly similar. This right over here and this right over here look kind of similar. So what we can now say and finally make our statement about epsilon and delta is that delta equals epsilon over 5. And this, you can say, can be regarded as one of the main statements in our proof. We can draw this function. So this is somewhat how the function would look like. And if we have a point right over there, 3, we can now be given a value of epsilon. So let's say the first player gives a value of epsilon like 5. I'm just going to say 5 because it's easy. Let's say he gives a value of epsilon like 5. We know that this point right over here is 17. So the first player says, I want to be a maximum of 5 units away from 17. So right over there and right over there. It's going to be 22 and it's going to be 12. Pretty straightforward. So now we have to choose some respective value of delta. So if epsilon is 5, we see that delta is 5 over 5, which is 1. So delta will now be 1, which is 2 and 4. So this is basically what it's going to look like. So when epsilon is 5, delta is 1. So you can say that delta is kind of dependent on the value of epsilon. And that's exactly what's supposed to happen. So how do we actually prove this? The proof is kind of weird. It's not as straightforward as you think. It's not hard either. It's just a kind of a weird way of actually proving it. So what we have done is evaluated this inequality right over here. So what we now want to do is evaluate this guy. So we can say absolute value of x minus 3 is less than delta. We can see that delta is equal to epsilon over 5. Therefore, the absolute value of x minus 3 is less than epsilon over 5. Now, because both of these are equal, we have proved the limit. I know it doesn't really look like we've proved anything, but this is what's regarded as proving a limit. When you prove that when you evaluate this, that equals to when you evaluate this. Basically, both of these are equivalent, and that is what you have to prove. Let's do another example. So let's say this is what we have, and we have to prove that limit as x approaches 0 from the positive side equals infinity. So because our L value over here equals infinity, we have to do some changes. So let's try and write this down as our regular restrictions. So we must say f of x, which is 1 over x, minus L. Now we can't really do minus infinity since infinity isn't really like a regular number or even a variable. So what we have to do is instead of 1 over x minus infinity is less than epsilon, what we do is 1 over x is greater than epsilon. Whenever we have a minus infinity, especially in this case, all we have to do is switch the inequality sign and it's all well and good. So this will be true when x minus 0, so we can just say absolute value of x, is less than delta. So once again, as always, let's start by evaluating this guy right over there. So what we can do over here is 1 divided by both sides. So 1 divided by 1 divided by x simply gives you the absolute value of x must be less than 1 over epsilon. Now these are simply inequality rules. When you take 1 divided by both sides, you have to switch the inequality. When you multiply negative 1 on both sides, you have to switch the inequality. So these are simply some inequality rules which are pretty simple and straightforward to learn. So let's move forward. Now what we can see is this looks a lot like this. So we can make our statement that delta equals 1 over epsilon. So let's draw the graph. This is the graph right over here, once again only in the first quadrant. I haven't drawn the third quadrant part since I'm taking it from the positive side. Now if I have any value of epsilon, the value of delta will be 1 divided by that value. Now because L is infinity, epsilon is quite weird because we can't really do infinity minus or plus any number. So this example may seem a bit weird, but this is still how you do it. If you graphically represent it, it does seem a bit out of logic as to why would this ever occur? Why would you ever add any value to infinity because you mathematically cannot? But anyways, let's just continue on with the proof. So now to prove it, all we have to do is take this side of the equation. Delta x is less than, absolute value of x is less than delta. Delta is 1 over epsilon. So we can say 1 over epsilon, and both of these are equal. Hopefully you understood that problem because as I mentioned, logic-wise, it doesn't really make much sense because if you have infinity, how can you add anything to infinity? How can you subtract anything from infinity? It doesn't make much sense. But math sometimes doesn't make sense. Let's do one last question. So let's say this is what we have over here. The limit as x approaches 4 of x squared plus x minus 11 equals 9. So once again, as always, let's first restrict our f of x. So we have x squared minus x minus 11 minus 9 must be less than epsilon when x minus 4 is less than delta. As always, let's start by evaluating that. We get x squared minus x minus 20 is less than epsilon. First thing to do, always factor. So what we get is x plus 5, that looks correct, must be less than epsilon. We have a problem because only this part looks like this. We still have an x plus 5 dangling in the distance. So what do we do with x plus 5? Now this is a little bit interesting. In order to get rid of x plus 5, what we have to do is assume the absolute value of x plus 5 is less than some value k. What? Now you may be thinking, what is the point of this? We do this so that we can get rid of x plus 5. So what we want to do right now is multiply both sides by x minus 4 so that we can get something extremely similar to this right over there. What we can now get is x plus 5 into x minus 4, absolute values and everything, is less than k into x minus 4. So now we can say, as you can see that this and this is equivalent, that k into x minus 4 is equal to epsilon. So now what we do is the absolute value of x minus 4 is equal to epsilon over k. Now what we have to do is a little bit tricky because we have to make a very large assumption. We have to assume that the absolute value of x minus 4 is less than some arbitrary number. You can have the number as 1, you can have it as 5, you can have it as 3,000, or 1 over 15. It's really your choice. But what I'm going to do is I'm going to say that the absolute value of x minus 4 is less than 1. Why am I taking 1? That's because 1 is an easy number to deal with. It's just overall, I guess you can say the easiest number. You can't say 0 because, well, the absolute value can never be less than 0. So now what do we do? The first thing we must do is try and morph this right over here to x plus 5. So how do we do that? Well, the first thing we must do is get rid of the absolute value symbol. So we can say that x minus 4 is less than 1 and greater than negative 1. Greater than negative 1 because it can never be negative, and therefore it can equal 0, but it can never equal negative. So now what we have to do is, once again, try and get this to be looking like this. So we add 4 on all sides, so we get 3 less than x less than 5. Now what do we do? There are a lot of steps to this, as you can see. We add 5 on all sides so that we can finally get our answer. 8 must be less than x plus 5, which must be less than 10. So we can finally put back the absolute value symbol. However, I must erase this because, as you can see, I don't have much space. Now, as you may be able to see on the corner of your screen, on the right corner, right-hand side, I do have a second whiteboard, but the camera unfortunately isn't able to go on that angle as of now with the setup that I have. So I'm just going to erase it and maybe leave it for another day. So what we can say now is the absolute value of x plus 5 must be less than 10. Do you see the similarities? We can now say that k equals 10. Because right over there and right over there, we can now finally do something with our lives and make something of ourselves. Anyways, so now what we can say is that the absolute value of x minus 4 must be less than epsilon over 10. And if you remember the stuff that I actually just erased, I should have kept that. The stuff that I just erased was absolute value of x minus 4 must be less than delta, right? We can get that from there. So finally, we can make our comparison and say that delta equals epsilon over 10. However, there's another thing we are forgetting. If you remember over here, I mentioned that x minus 4 absolute value must be less than 1. Therefore, delta does not necessarily have to equal epsilon over 10, but can also equal 1. So you're saying delta has 2 values? Not exactly. So what we generally do when delta has 2 values like this, all we have to do is that delta equals the minimum value of epsilon over 10 or 1. Depending on which one is lower, delta will take that value. So by doing this, we kind of, you can say, guarantee that delta will be one of these values. Hope that made some sense. Okay, so finally, let's prove it. So what we have now is, as always, we take this value over there, we have the absolute value of x minus 4 must be less than delta. We have delta equals epsilon over 10, or it equals 1. So the absolute value of x minus 4 must be less than epsilon over 10, or must be less than 1, both of which were proved in the function side of the inequality. I really do hope that made sense. This example by far is definitely the hardest one that we've done in this video. So I really do hope that you understood this, because when we're dealing with quadratic expressions, we generally do have 2 answers. Cubic, 3 answers, and it just goes up from there. And you have to do a very similar job by just assuming a value, such as 1, and then getting rid of the other values. So the other values you can simply do is must be less than k, must be less than a, b, c, whatever. The variable doesn't matter. One very big thing in limits is simple assumptions. You have to assume a certain number of things so that you can actually get the final answer. As you've seen in this, if we assumed a different number over there, the value of k would change, obviously. So we have to remember to keep our assumption and remember that there is another value in the end, so don't forget about it. I really do hope you enjoyed that video, maybe understood something about epsilon-delta limit definitions, and really understood how and where they can be used. Thank you so much for watching, and until next time, stay sharp.